streaming, and then Discord just crashed right when I joined the voice chat. So I'm gonna reshare the screen. There we go. Go live. All right. So I think everything should be good. Yep, okay. So YouTube is getting the stream, and Discord is streaming as well. And we got 4 people, joining me live on Discord, and hopefully a few more on the YouTube channel. So I know the semester is, we are past the middle part of the semester. So this is the last stretch of the semester. So I'm definitely hoping people are kind of like keeping it up, to get to the end. All right. So are there any questions about the topics from last time? Oh, okay. I'm just reading the comment. You guys definitely have a choice, to watch it either way. Asynchronous or synchronous. I make the synchronous part optional for this class, which means a whole lot of people can decide to watch it in an asynchronous mode, which makes it kind of difficult to ask questions. But it's okay if if that's how the timing is going to work out. Cool. All right. So now let's move on to the topic. Okay, so we're basically just continuing on where we left off from Tuesday. And on Tuesday, we talked about counting. Okay, so let's open up this in its own browser. There we go. And we were only talking about section 4, and then I kind of illustrated why it is important to understand how to count the number of possible outcomes when we have experiments that are without replacement, when each trial is without replacement. So that means when an item is chosen by an earlier trial, that item is no longer available for later trials. And the explanation of why it is important to be able to count these things, well, I mean, the lotto game is a pretty good reason. And then almost all card games, okay, involve some sort of probability distribution that also has to do with counting the possible outcomes of an experiment where the trials cannot are without replacement. Okay, the number of choices or the number of outcomes for each trial is without replacement. Once something is chosen, it is gone. All right, so what we'll do now is to take a look at the formality, of the notations, and then we'll get to the section that is not this one. Section 5 is pretty easy, but section 6, is going to be the one that is that's going to be a little bit complicated. So we'll go ahead and talk about the notations first. All right. So let's go ahead and explain, the notations here, particularly this one here. What is this doing? I mean, this big U, with apparently, some kind of, loop doing this. So what this is doing, okay, so let's just read from the beginning. A common restriction to trial in one experiment is whatever is chosen earlier cannot be a choice later on. So that is why it is called without replacement. So T, without any subscript or any notation otherwise, is representing the set of all outcomes for the first trial. Okay, so we start with these items to begin with. And we'll use M to represent the number of trials in a particular experiment. So it kind of goes without saying that M cannot be greater than N because you only have N objects, right? So if you have an experiment where each step is removing N object, then you cannot have, N, which is the number of, excuse me, I take it back. So you cannot have M, which is the number of trials, being greater than N, which is the number of objects in a bag. So now we continue to look at, E bracket 0 or E subscript 0. I use a subscript 0 here to basically emphasize that E0 is what we chose in trial 0. Now, trial 0, is actually the first trial. It's just that, in computer science, we count from 0. So I use E0, E subscript 0 to denote that this is what we have chosen in trial 0. Okay. Now, obviously, depending on your actual experiment, E0 can be any one of the elements in T. Okay. So when we look at trial 1, okay, so when trial 1, remember, is the second trial. Okay, it's not the first trial. It's just that we count from 0. So trial 1 is going to have an outcome set of T minus, in a set E0. Well, that kind of makes sense, right? Because E0 is already chosen by trial 0, and as a result, it's not going to be available to trial 1. And as a result, T minus the set of E0, if you look at the cardinality, well, that's pretty simple. It's just going to be N minus 1. And as a result, we have N choices for trial 0. We have N minus 1 choices for trial 1. And then we have N minus 2 choices in trial 2, and so on. Okay. So do we have any questions about the notations or what these numbers are representing at this point? I'm just looking at the Discord text channel, and there does not seem to be any questions. All right, so I'm going to continue here. So I'm just extending, so now I use E subscript I to represent the actual outcome set of trial I. Okay, in other words, what choices is left, okay, when I get to trial I. And remember, we count from 0. So in a particular experiment, okay, the outcome set of trial I is going to look like this. T, once again, is representing the number of all the outcomes for trial 0. Okay, initially you're given all of the choices. This big U notation, look at this kind of as a sigma notation, because it's basically just a loop. Okay, it's a loop to form a big union of individual sets. In this case, each individual set in the loop is really just a singleton set, which means the set only has one particular element. And that particular element is E subscript j. J is going from 0 to I minus 1. In other words, we are basically just excluding elements of T that were chosen already by previous trials. Whatever is left is available to trial I itself. So let me just kind of pause here to make sure that everybody has an understanding of the notation, particularly the big U notation, which is basically just a union over a loop, where index j goes from 0 to I minus 1 in this case. So I'm going to give you guys a few seconds to ask any questions. All right, I am not seeing any questions. All right, so if I'm not seeing any questions, I'm just going to continue, okay? So continuing, in this particular section, I'm only interested in counting. In other words, I just want to know the number of possible outcomes in an experiment. I don't need to know what each outcome looks like. I just need to know how many there are. So as a result, I'm not really interested in this particular set. I'm much more interested in the cardinality of the set. Well, the cardinality of the set is really just n minus I. Nope, it is not n minus, and then in parentheses I minus 1, because we count from 0. Okay, so if you count the number of iterations in the big U notation, because j goes from 0 to I minus 1, so that means we have I iterations, in this case, and as a result, n minus I would be the number of elements left within the set that is denoted here. So are we okay so far? All right. So every time we see a generalization, something that looks like this, where I is representing, which trial we are talking about, it's good to double check everything and see if it makes sense or not. Okay. So let's just say that I equals to 0. Okay. We want to see whether that makes sense or not. So when I equals to 0, t is still here, right? But then you look at J, and J looks kind of funny now because J as an index of a loop is going from 0 to I minus 1. But remember, I is 0, so I minus 1 is -1. Oh, so that means we're not going to go through any iteration because the implicit way of changing the index is we are only incrementing, we are not decreasing. So as a result, we have 0 iterations through the big U notation, which also means this entire big U part is giving us an empty set. So the entire T is back, and that gives us really just n, right? Because I isn't 0. So the question is, do we have n choices or n possible outcomes for trial 0? By definition, yes, right? Because by definition, n equals to the cardinality of t, and by definition, t is the set of all possible outcomes of trial 0. Okay, because those are the things that we're given with. So after we check, okay, this is kind of like a sanity check. It's not really a proof, but it's a sanity check to show us that this notation seems to make sense. Okay. Now, if that seems to make sense, then we have we have a big pi notation. So big sigma is for summation, and then big pi is for multiplication. So in this case, we have a multiplication. Okay, on this side we have I as an index variable this time to m minus 1. So we are basically looking at m again as the number of trials. So I only goes from 0 to m minus 1 and not all the way to m because we count from 0. So as I goes from 0 to m minus 1, we'll go through that loop exactly m times. And each time we go through that loop, it is representing one particular trial in this experiment. N minus 1 over here is really the cardinality. So we want to evaluate what this number looks like. And if you want to go through the math, you're more than welcome to. But in the end, what we end up with is n factorial divided by n minus m factorial. And that also has a name of p and m. And I made a mistake here. I took out the equal symbol, and it just doesn't look right. Okay, so let me fix that on the side right now, because I don't like to leave it unfixed when I can see there's a mistake already. I have been working with this section a little bit because initially some of these superscript, subscript notation did not show up correctly. So because when I was experimenting with those things, I made some changes, and as a result, that stuff does not show up correctly. So I'm gonna put this back here and specify that and take that out. Okay, so I think that should fix it. All right, so things should be uploaded. Let me just refresh everything. There we go. And now it still doesn't look right. It's supposed to be on its own line. So let me fix that too. There we go. All right, there we go. So this is the notation. So when you ask a mathematician This is what this is. They recognize this notation. Okay, it's P, which stands for permutation, with a superscript of n, and that represents how many items we start off with, and has a subscript of m, which is the number of trials in a particular experiment. And P and M is counting the number of permutations of choosing m items out of n. Okay, so let's pause here. Okay, and let me see if there are any questions from you guys. All right. All right. Yeah. E is really just the prefix of an element. So E of I is the element in the set of T that we chose in trial I. It's just an item. All right. And we got a few questions on the side. N is starting number of items. Yes. So N is the number of items that we start off with. So in the game of Super Lotto, there will be 47 because the numbers can range from 1 to 47. So when we pick the first number, it can be anything from 1 to 47, and therefore there are 47 items to choose from. And then Kevin is asking, what is the LaTeX for that symbol? And I'm suspecting Kevin is referring to big NM. I mean PNM. Is that correct? All right. No, the one that looks like pi. Oh, that's just pi. That's pi with an uppercase P. So the really cool thing you can do now, okay, is you can actually right-click, go to Show Math As, and then go to LaTeX command. And this one is going to look pretty nasty. Oh, I take it back. It's not pi. It is \prod for product. So I stand corrected. And the cool thing is you can try it out. Okay, you can copy the clipboard like that, and then we can go to, I'm just doing this on Discord. And in Discord, I'm not sure whether it's $double or $single. Let me just try $single first. It's double. Okay, so $double, and then Control V to paste this entire thing, and then $double again. Let's see if that works. Yep, MathBot is working on it. Oh, okay, it doesn't like it. I think it doesn't like the aligned environment, and that's why it chews me up. Okay, if I do a \prod, I'll just use underscore X and then superscript caret Y and then $, and see if that is rendered correctly. Okay, there we go. So it does work correctly. It's just a \prod, P-R-O-D, with an underscore to indicate what goes under, and and caret then to indicate what is over. So I hope that answers Kevin's question. It means multiplication in a loop. Okay, so let me answer that particular. Yeah, go ahead. Let me put it this way. Let me use a regular editor in this case. Mousepad. There we go. All right. All right. So I am just gonna make an equivalence between the concepts. So if I have big pi, okay, prod, and underscore is I equals to I want to give it a range here, but I want to make it a variable. So I'll just go, it starts with A and it ends with B, okay? And the term that I am multiplying together, I'm just going to say it is a function of I, okay? So I'm just going to use f of I to indicate what I am making a huge product out of. So this would equivalent to the following code. So it's going to equivalent to the following. I would call it pseudo C code. So it's going to say, for I equals to A, I is less than or equal to B, because we want to include the iteration when I does equal to B. And then for each iteration, we want to increment I like that. We also need a local variable, I'll just call it, let's make it a double, because f of I can return something that is not an integer. So product, this is my initial product. So product has to be initialized to 1 to begin with, because 1 is the identity of multiplication. And then in the loop for each iteration, all I am doing is to say product equals to product times f of I. So this notation, especially if you look at it, when you view it as a big pi notation, is really doing the same thing as what this code here is doing. And the value of the big pi notation is going to be just product itself. So does that answer the question? Hmm? Oh, yeah, sure. So let me Control A, Control C, and then go to Discord and tick, tick, tick. Okay, back tick 3 times, and then paste here, and then back tick 3 times again to end the quote. There we go. How does that work? And of course, I can also, include the pi notation. So I'm just going to do that part too. This is why I like Discord, because there are no, I'm not aware of, I shouldn't say there are no, but I'm not aware of any other platform where I can install a bot so that I can convenient. Oh, that didn't work because I forgot about the backslash. Okay, let me go back, and this is the other thing that's really cool. You can go back and edit a message that has LaTeX notation, fix it, and MathBot will render again. This time it is correct. There we go. So I hope that works, right? So I show the C code and also the mathematical notation that is corresponding to the C code. All right. So getting back to here, so once we understand what the big pi notation is really, it's really just a loop, right? I as an index variable goes from 0 to m minus 1 and incrementing by 1 for each iteration. And this is our f of I, okay? Our f of I is super simple. F of I is defined to be n minus I. And the rest of this, okay, is really just, playing with the indexes of the pi notation. That's all I am doing here. So with the first step, okay, I do want to explain this, because I want you guys to start to get familiarized, excuse me, with the big pi notation, the product notation, and also how to deal with things like this, how to simplify and how to manipulate so that in the end you get a quote unquote closed form notation. So in the first step, all I did was to say, hey, this thing here, okay, it looks kind of icky, but nonetheless, it really is just 1 because I have the same thing for the numerator as the same as the denominator. So it's really just 1. But what is interesting about this is if you look at this particular pi notation, the one in the fraction, it is a continuation of the one that is on its own, the original pi notation. Because in the original pi notation, now first of all, the function has to be the same. So n minus I, n minus I. So that part has to match first. The second part is this one I goes from 0 to m minus 1. And then in this one, I goes from m to n minus 1. So in other words, this pi notation is really just a continuation of this pi notation here. So I can now combine the pi on the outside of the fraction and the numerator in the fraction and say, hey, that's just really kind of a longer pi notation. And that longer pi notation has I, the index, going from 0 to n minus 1, because m minus 1 and m are right next to each other. So we basically just say, hey, there's no need to separate the the big product into two parts. Okay, we can combine those two parts. So when we combine those two parts, then we have this notation here, and then we say, hey, n minus 0, excuse me, n minus 1. Okay, 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 let me put it this way. When I equals to the last item, which is n minus 1, then n minus in parentheses n minus 1 close parentheses is just 1, right? It doesn't contribute anything to the overall product. So I just shift things around a little bit. So I end up with from here I go to here. So I, instead of going from 0 to n minus 1, I now have I going from 1 to n, okay? Because it makes sense, okay? When I does equal to 0, it contributes n as the term being multiplied. When n is when I is n minus 1, then the term inside the parentheses is just 1. In other words, I'm just multiplying everything from n all the way down to 1. So this is the more obvious way to write it, okay? And I do the same thing on this one, and it becomes I going from 1 to n minus 1. So from this to here, I change the term or the expression that I am multiplying over, but also at the same time, I also adjust how I express the index accordingly. So now it's just I itself. So I can now say, hey, if I want to multiply 1 all the way to n, there's a known notation or called factorial for that already. And the same thing for the second one, which is if I want to multiply 1 to n minus m, we also know that that is just n minus m factorial. So P and M, or the number of permutations of choosing m items out of n, is just this, okay? It's just a shorthand of writing this out. All right, so are we good with the notations at this point? And also why the number of permutations is n factorial divided by n minus m factorial. All right, I'm not seeing any questions. Let's move ahead then. All right, so the next section talks about ordering, which is something that we also talked about on Tuesday, because the idea is in certain situations, okay, we do not want to count separately when items just they have this, when tuples have the same items in them, we don't want to count them separately. So that is that's the reason why P and M sometimes it will give us a number that is way too big, because when we look at lotto tickets, okay, when we look at the possible number of lotto tickets, the ticket of 1, 2, 3, 4, 5, is representing the permutations of 5, 4, 3, 2, 1, 1, 2, 4, 5, 3, and so on. So it doesn't matter, okay, if we are choosing 5 lucky numbers from 47 ones, it doesn't really matter, which one comes out first and which one comes out last, okay? All we need to know is which 5 numbers are the lucky numbers. How they are sequenced in the process of drawing the numbers doesn't really matter. So now we need to say, okay, so that means, when we actually watch, okay, how those numbers are drawn, there are a whole lot more ways of, taking those balls out of the basket than there are actual lotto tickets. So now the question is, so if we can count how many ways we can draw 5 numbers out of 47 when sequencing is important, okay? How do we convert that to the number of just, okay, how many ways can we draw 5 numbers out of 47, but ordering is not important? So we're trying to get rid of ordering in this case, and basically do a count of how many ways can we choose 5 out of 47. So the idea of chapter 5 is not to look at the 47 numbers anymore, okay? We focus on just 5, okay? So we're going to say, okay, just look at, for instance, okay, this is just an example, okay? So for instance, 1, 2, 3, 4, 5 are the lucky numbers, okay? But we know that, given that 1, 2, 3, 4, 5 are the lucky numbers, there are many ways to draw these 5 numbers out of, the basket. So now the question is, how many ways can we do this? So the answer to that particular question is actually a question that is answered by section 4 itself. Because when you have 5 things and you want to choose all 5 things and you want to look at the number of permutations, then you have basically P of 5 as a superscript and 5 as the subscript. So then you plug it in, right? You plug it into this equation here. N is 5, so we have 5 factorial. And then n and m are the same. So we end up with a 0 factorial as the denominator. 0 factorial is by definition 1. So we really just have, oh, that's just 5 factorial. Oh, okay. So that means, okay, so what that means is if you're given with the number of permutations, but you're only interested in the number of combinations, because one combination is basically a set where ordering is not important, then all you have to do is to divide the number of permutations by m factorial. Then you get the answer. Okay, so by the end of here, we basically end up with a new notation, C and m is representing the number of combinations of choosing m out of n, which is also written like this. Okay, I know it's really hard to write it like this with a text editor, but basically what it boils down to is the number of permutations of choosing m out of n, and then divide the entire thing by m factorial. So when you expand the equations, this is what it looks like. So it is n factorial as the numerator, and then we have m factorial times n minus m, the entire thing factorial. That basically becomes the equation. This is the equation here. C and m is defined as n factorial divided by m factorial times n minus m factorial. I'm just gonna pause here and see if there are any questions. So if you have any questions, please go ahead and either type it out or use the voice channel and let me know. All right. You mean to illustrate how the numbers work out? Okay. Let me think. Okay. How about an example? That will work. So we're going to look at an example as in a spreadsheet format. And I can do it the same way as last time. So let me go to my Google Drive. And go to the share folder. So you already have access to the shared folder for this class. And I'm just going to create a new spreadsheet. And the name is based on today's date, so that way it's easy to find it. And you can open it at the same time too, once I save it. 2020, 1029. There we go. So now you can actually open it on your side as well. So what I'm going to do is to illustrate with an example. Okay, so we say n equals to 4, and we'll say t, which is representing the outcome set of the first trial, to be simply A, B, C, D. Okay, so that makes sense. Okay, and we want to make m equal to 2, which means we're choosing 2 items out of these 4. Okay, so the first thing we want to do is to look at permutations, where ordering is important. if I choose A first, then the second one I can choose B, C, or D. So A can pair with B, C, A, D. Okay, and if I choose B to begin with, the next one can be A, can be C, can be D. If I choose C to begin first, then I have A. I can have A as the second item. Then I can have CB, and I can also have CD. And last, if I choose to start with D, then I can have A as the second item. I can have B as the second item. I can also have C as the second item. So is that okay? When we are just looking at permutations. Okay, excuse me. So when we look at these permutations, so we can now see P of, let me see, the first one is N, which is 4, and the second one is 2, is, I mean, you can do the counting here, right? So you can count and say, oh, there are 12 of these, but you can also use the equation, which means, we're looking at 4 factorial divided by 2 factorial. Now, this 2 factorial is not really referring to this 2 over here. It is actually referring to 4 minus 2. So let me make that extra clear that we are looking at 4 minus 2 factorial. And if you look at 4 factorial, it is 24. If you look at 2 factorial, it is 2. So if you do the computation based on just the numbers, you end up with a value of 12. But if you count the number of actual 2 tuples in as permutations, that's also exactly 12. In other words, the equation seems to work. So now we want to look at combinations. Okay, combinations is basically, each combination is a set. So that means this is corresponding to the set AB. Now, when we look at permutations, each one is implicitly a 2 tuple. But when we look at combinations, each one is implicitly a set. Then you go like, hey, but Tack, hold on a second here. There's another AB in here, except it just looks like BA. Oh, okay. So now we can see how these 2 permutations are corresponding to the same combination, right? And we look at AC, okay? So it corresponds to the set AC, but there's also CA all the way down here. So these 2 are really corresponding to the same. So if I want to... what do you mean by... We are not counting it twice. I'm just looking at each one as a combination at this point, okay? So I look at this as AD, and then this is also AD, and so on, right? So in the end, when I try to make a big, huge union to combine all of these items, then you will see that, oh, but exactly what Aaron said earlier, this item and this item can only appear once in the set of outcomes, because each outcome is now a set, not a 2 tuple. So these 2 can only be counted once. These 2 can only be counted once, and these 2 can only be counted once. In fact, if you look at each way of each particular set, it will give us exactly 2 permutations. So the number of permutations is now, okay, if you look at the combination C42, it is going to be P42, but that's going to give us, way too many counts, because we know that each set here has 2 permutations corresponding to it. So now you also have to divide it by 2 factorial, and that becomes it becomes 6. So there are 6 ways to choose 2 things out of 4 when ordering is not important. Why do we choose 2 factorial over 2? Not sure. Not always, because it depends on it depends. Okay, so if you look at lottos, right? Okay, so let's take a look at lotto numbers. Lotto, super lotto in this case, actually super lotto plus example, but we're only looking at the lucky numbers. So the lucky numbers, so basically we draw 5 out of 47 numbers to be called lucky. Okay, so let's just say that we, for whatever strange reason, we choose. We know these are the members of the lucky numbers. We know 1, 2, 3, 4, 5 are the lucky numbers. Then you ask, so in terms of a set which only cares about membership, is it there or is it not there? Now, if you look at the actual process, okay, of how many ways can we choose 1, 2, 3, 4, 5 in a sequence, okay, out of a basket, then there are many ways to do this, right? Because now we can say, oh, corresponding to this particular set, okay, how we end up with a set of 1, 2, 3, 4, 5. The sequence of choosing these things can look like exactly 1, 2, 3, 4, 5, where the first number drawn is 1. But I can also choose 2 first, and then 1, 3, 4, 5, right? I can also choose 3 first, and then 1, 2, 3, 1, 2, 4, 5, and so on. So now the question is, if I somehow end up with a set of 1, 2, 3, 4, 5, which means these 5 numbers are the ones chosen out of 47 to be called the lucky numbers in Super Lotto Plus. The question is now, how many ways can I end up with that collection of lucky numbers? So when you look at these items here, how many are there? That becomes the question. But that's an easy question to answer because we already talked about permutations, right? So we know that there are P55 of ways to choose 5 numbers in a sequence. So when you add up all of these things, it becomes P55. And P55 is really just 5 factorial. And that is, if I remember correctly, 120. So for the set of 1, 2, 3, 4, 5, there are 125 tuples that will contain exactly the same elements, the same values. Is that making any sense? No, it's the other way around. When we count permutations, we are actually counting the number of tuples. When we count the number of combinations, we're actually counting the number of sets. Yep. So you might for the entire class, okay, this is something that I did not write in the notes, but in your own notes, you might want to write down, to basically, just indicate that permutations are related to tuples, and then combinations are related to sets. Because I think that is a kind of important distinction, but it's also utilizing concepts that we have been talking about quite a bit in this class already. So it's not just helping you to understand the current topic, but it's also reinforcing how much you understand with the previous topics. All right, so if this part is okay, we're going to continue with the notes. There we go. All right. And let me just kind of scroll back to the portion about CNN. So do we have any questions about P versus C? In other words, the concept of permutations versus the concept of combinations. In a lotto game, we are only interested in the number of combinations because permutations is not we don't care about the ordering in that case. So can someone give me an example where we are actually interested in the ordering of the items, and not just whether it is there, but we also need to know in what order are they, how are they sequenced. So I will give you guys a kind of a little bit of time to talk about it. In Blackjack, yes, so Blackjack is important. Okay, I'm glad that somebody is using a card game. All right. Remember traveling salesman problem? Okay, so let me just kind of, okay, very good. So, but I will go ahead and just kind of remind everybody about the traveling salesman problem. So in the traveling salesman problem, we basically say there are n cities that a particular salesperson, okay, I guess salesperson is the more politically correct term these days. So we'll have we'll call this traveling salesperson Pat, okay, to be even more politically correct. So Pat has let's say 16 cities, okay, to go through to sell something. But the company, who hires Pat, okay, has certain travel restrictions, okay. One restriction is, Pat can only visit one city one single time, okay. So, except for the home city. So Pat will go from the home city to each one of those, 16 cities, and then come back to the home city. But he cannot, Pat, oh, I cannot say he, but Pat cannot, um, go to Atlanta, and then go to somewhere else, and then go back to Atlanta, and Atlanta is not the home city. So each city, other than the home city, can only be visited exactly once. Okay, so these are the rules. And now the question is, how can Pat optimize, or how can the company optimize, the traveling plan for Pat? That's the question. So it doesn't sound very complicated, right? Because that seems pretty easy. But in reality, it is actually not a very simple problem to solve, especially if those 16 cities are kind of all over the place. So you can use heuristics and go like, okay, well, basically clump the cities, okay, the ones that are kind of close proximity to each other, will clump it together. But that is not going to give you the optimal solution. So the optimal solution in this case is to look at every single way of traversing the 16 cities, and evaluate how much it's going to cost for that particular way of traversing. So in this case, we'll be looking at the number of permutations. And there are 16 factorial permutations in this case, because we need to visit every single city. So there are 16 factorial ways of traversing the 16 cities. So the extreme opposite of this is the number of combinations. In other words, what is the number of combinations when we need to visit all 16 cities? There's only one, okay? Because combination is a set, right? We want every single city, all 16, to be in this particular set. So how many ways can I choose 16 items out of 16 items? There's only one way when the ordering is not important, okay? So when you look at C, and N and M turn out to be the same, it becomes one, okay? The number of combinations becomes one. Blackjack, does take into consideration of ordering, so we'll be looking at permutations instead of combinations. Any other examples you guys want to give, kind of share with the rest of the class? No? All right. So we're now going to move on. Okay, we have about a little less than half an hour left. Okay, so if you do have any questions about the concept of permutations versus the concept of combinations, now is a good time to ask, because section 6 and section 7 are nasty, okay, in terms of the notation. In terms of concepts, it's really about the same as the previous sections, but in terms of the notation, it gets a little bit strange. All right, so if there are no questions, we're going to move on to section 6. So section 6 is not concerned about counting. It is actually concerned about what does the set look like, okay? So section 6 is only concerned about permutation. So if I give you items, okay, so once again, we can go back to, oh, not this one. So we can go back to the spreadsheet that we were looking at, okay? So section 6 is basically saying, if I know that 1, 2, 3, 4, 5, these are the items that I start off with, and I want to choose all 5 items, but ordering is important. How many different ways can I get 5 items out of a bag when ordering is important? Okay, but we switch. Okay, instead of asking how many ways, now we ask what are the exact ways of choosing 5 items out of a bag. In other words, we want to end up with these 5 tuples, each and every single one of those. So now the question is entirely different, right? Because it is not about counting anymore. It is about the actual generation of these permutations. So does anyone have any questions about, or any idea of why sometimes we are interested in the actual permutations and not interested in the number of permutations? Okay, let me take a look at the Discord side and see if there are any questions. There are no questions. Oh, really? Okay. Let's think about assessment, okay? Exams and tests. And let's think about these from your other classes, okay? Where the professor says, I'm just going to turn on, something that the publisher is supplying me with, multiple choice test, and so the professor doesn't have to do a single thing, lift a single finger to create the assessment, nor to grade it, okay? Because everything is going to be automatically graded. But then the professor says, but I really kind of want to make sure that people, cannot collaborate, okay, not easily. So there's a feature in Canvas to randomize, okay, the ordering of questions. So we're still looking at the same questions. It's just a different ordering of the questions. So now the question is, how does Canvas generate those variations? Does everybody understand what I'm talking about? Okay, so if not, I can just kind of give a quick illustration here. So let's think about a very simple test, okay, where we have 4 questions, okay? So the 4 questions are, I'll just say, is A, B, C, and D. So these are the 4 questions in a question bank. And then the professor says, I don't want these questions to be ordered exactly the same way for everybody. I want it to be different, okay? I want to have variations from one student to another student. So that professor will turn on a feature in Canvas, that will basically, change the ordering. So now we look at things from the perspective of Canvas, okay? How does Canvas, generate all these variations? Okay, so if I were to kind of illustrate, those variations, ABCD is one, ABDC is another one, and then we have ACBD, right? And then we have ACDB, and then we have ADBC, and then we have ADBC, and then we have BACD, and so on. Okay, so now the question is not how many there are here, because we already know the number is 24. The question is, how do we generate these permutations using a program systematically? That is the question. But does everybody see the application of this? Sort of. Okay, so, okay, excellent. So now we go back to the module, because the module actually contains the code to do it, but nothing in this section looks like code, right? So that's why we need to kind of look into the definition of the symbols kind of really carefully. The first thing we do is to understand what is T subscript I. T subscript I is the number of outcomes that is available to trial I. Okay, so it's the same notation as last time, okay? But this time we are not interested in the cardinality. This time we're actually interested in exactly what is in T of I. So the question of that is a little bit tricky now, because it depends on what happened to the previous trials, because depending on what items are chosen in previous trials, T of I can change. Okay, it's not fixed. With a particular set, it has to do with what we have already chosen in the previous trials. The outcome set of we call omega of an experiment of m trials is the Cartesian product of the outcome set of these, but this is only when well, let me see. It is not exactly the Cartesian product anymore. It is a Cartesian product when it has replacement, but without replacement, it is no longer a Cartesian product. So this paragraph here is applicable when things are with replacement. But when things are without replacement, it gets a little bit awkward to express. So starting with this paragraph here, it says, let T represent the pool of choices, or set. Okay, when you see the word pool, you can equate it as set. So T is representing the set of choices, or you can say outcomes, that is available to trial 0, okay, the first trial. And we also use this notation here, omega I of T, to represent the outcome set of an experiment involving I trials, starting with T as the set of trial outcomes. All right, so let's just look at this part again, because this is new. Okay, we haven't used this notation before. Omega I is representing the outcome set of an experiment that has I trials, and for the first trial of those I trials, the outcome set is T itself. That's basically what this symbol is representing. Now, because we have a set of permutations, so you can look at it as a set of tuples. Okay, so omega I of T is a set of tuples. And when a tuple is singleton, we just basically say that it's the same as without a tuple. So it is kind of easy to see how, or why omega 1 of T is just T itself. Because we are looking at the outcome set of an experiment that only has one single trial. So whatever is the outcome of that one single trial is now the outcome of the entire experiment. Does that make sense? I just want to make sure that everybody is understanding this part here. Because I equals to 1, so we only have one single trial. When an experiment has one single trial, then whatever is the outcome set of that one single trial becomes the outcome of the entire experiment. Is that okay? Does everybody understand that part? And this time I'm going to wait a little bit, because this is a very important concept, because this is forming the end of a recursive definition. So we have to know when we stop the recursive definition. All right, so I'm still not seeing any questions. Now, if you just need more time to absorb the material, you can just go ahead and let me know, either by the class text. Sure. Okay, so let's take a look at, okay, see, I'm just trying to find the best way to express that. Okay, so I'm just going to use this, text window here. So this is my way of separating the two. All right, so we'll just say t equals to, let me see. I don't want to make this overcomplicated, but I also want to make this so that it is relevant to people. So I have to think of an example where ordering is important. Okay, so let's think about Blackjack. Okay, and is Blackjack the one that has to count to 21 or 10? I cannot remember. 21. Okay, and so Queen is considered 10, right? Queen, King, Ace,
Yes.
they're all 10s. Is Ace 1 or 10? Ace is 1, right? Or 11. Oh, okay, so it can be both. Oh, that throws a wrench into the counting part. So let's just say that Ace is 1 for this discussion purposes, okay? All right. So T is going to have all the cards, and we'll just say that, we'll simplify the game a little bit. And let's just say that at this point, T is, we can have a queen, we can have a king, we can have a 2 and a 9. Okay, so for whatever reason, these are the only 4 cards left. Okay, so omega 1 of T is basically asking, if we are to draw 1 card. Okay, now this 1 here is basically the same as this 1 here, because the subscript of omega is telling us how many trials we have in this experiment. So in this case, there's only 1 single trial. We're only drawing 1 single card. Okay, so the question is, if we are to draw 1 card from T, what are the possible outcomes? So the answer to this question is, oh, that's easy, okay? Because if we are to draw just 1 card out of T, then it would just be T itself. Or if you really want to be, anal about the notation, it's going to be tuples that only has 1 single items. Does that make sense? Okay. So now, if I ask another question, now, so in notation purposes, for notation purposes, I'm just going to look at this and say, hey, when we have a single item, whether it's a tuple or not is not important as in this discussion. So we'll just write it as if there's no tuple notation. Okay. So now, if I ask what is omega 2 of T, now this time I'm not going to go for the recursive definition. We'll just kind of work it out. Okay. Because what omega 2 of T is asking is, well, it's kind of the same thing, except instead of 1, it's now 2. Okay, so if we are to draw 2 cards from T, what are the possible outcomes? But in this case, you have to remember ordering is important. Okay, so we are choosing 2 out of T, but we need to know what order they're in. So, all right, so let me see if, okay, indentation is not automatic. That's okay. Let me turn that on and see how we can turn on auto indentation. I guess it's going to be in increase indent. Oh, okay. Does it keep it? Nope. Okay. So I want to, because otherwise I'm going to spend a lot of time indenting lines. Editor, tab automatic indentation. There we go. All right. So now we'd say we can draw a queen first and then a king. We can draw a queen first and then a 2. We can draw a queen first and then a 9. Or we can draw a king first and then a queen. We can draw a king first and then a 2. Okay. I mean, you guys are getting the idea, I'm pretty sure, but I'm just going to complete this whole thing. Okay. We can draw a 2 first and then a queen, a 2 and then a king, a 2, and then a 9. Or I can draw a 9 first, then a queen. Draw a 9 first, and then a king. Or 9 first, and then a 2. Is that okay? Does everybody see why omega 2 of t is going to look like this? Okay, so we are now understanding the notation of what omega I of t is representing. So as I goes up, you can see that the set will get larger, but each tuple in the set will also get longer. Okay. In other words, yeah, go ahead. We are not adding a set. That's the thing. Okay. So getting back to the notes here, okay, the way we look at omega 2 specifically is to say, what does omega 2 actually look like? It is, okay, I know this notation looks kind of weird. So basically we are looking at every element of T and then make a big union out of it. And what is each item in the union? The first thing is we have okay. First of all, is a Cartesian product, which means we're creating a set of tuples. So in this case, the first set out of the Cartesian product is a singleton set of E itself. Okay, and E is just whatever is coming from T. But what we are using as the second part of the Cartesian product is T minus E. In other words, we have chosen E already for basically this is what omega 1 has chosen. I mean, the first trial has chosen. And this is what is left for the second trial in this particular setup. So let's go ahead. Let me go ahead and copy this notation into, oh, I can show both at the same time. That's even better. There we go. Okay. So let's expand this particular notation and basically try to understand what it is talking about. So we have omega 2 of t being equal to a loop, right? So E in t as a loop is basically just an iterator. Okay, I'm not sure how many. Oh, I forgot. CISP440 is a co-requisite of this class, so I can actually assume that now. So I assume you guys know what is an iterator. Basically, we're going through every single element of T in the big loop here. So that means we have 4 iterations. The first iteration is when E equals to queen. The second iteration is when E equals to king. Then we have E equals to 2, and then E equals to 9. So there are 4 iterations corresponding to the big U notation. And we also know that we are just making a big, huge union for all of these cases. So we know that eventually, whatever we end up with in between, we're just going to union with the next item. Okay, I cannot, I suppose I can use the big U notation, but the big U notation can be confusing. So I'm just going to type out the entire operator of union. So now, what are we making a Cartesian product out of? Okay, so in this case, we are using queen as the singleton set here, and we are making a Cartesian product out of t minus queen. In other words, everything other than queen can stay in the set that I'm typing right now. So that would be king, 2, and 9 in this case. And then on the second row, which is corresponding to the second iteration, it will be king as the singleton set. Cartesian product with everything except for king. So we have queen, 2, and 9 in this case. And then on the third row, t equals to 2. So we have singleton set of 2, Cartesian product with t minus 2, which is king, queen, king, and 9. And wrong notation here. All right, and then the last row has 9 being E, Cartesian product with everything except for 9. So we have queen, king, 2, just like that. Okay, so does everybody understand how I just expanded the loop, which is implied by the big U notation, so that now we're looking at what happens with each iteration of the loop. Okay, so now we're going to expand the Cartesian product this time. So we'll go ahead and continue with this and then just use indentation over here. All right, so now all we want to do is to expand this portion here. So when we expand this portion, I'll make the expansion on the side and then delete it, delete the original. So all we're doing is to say, oh, let's make a whole bunch of two tuples where queen is the first item, and then we'll have king, 2, and 9 as the second item in these particular two tuples. So we have qk as one two tuple, we have q2 as one two tuple, and then we have q9 as the last two tuple. And once we have the expansion done, we don't need to look at this anymore. So we have this. And then on second row, kind of the same thing, except, in this particular set, we have two tuples where everything starts with king. And then the second item comes from the set, the right-hand side of the Cartesian product. So now we have KQ, we have K2, and we also have K9. And once we have the Cartesian product expanded, we get rid of the Cartesian product expression itself. And the last one, second to the last one, is going to have everything starting with 2. So we have 2 queen, 2 king, 2 9. Okay, get rid of that. And on this one here, we have everything starting with 9. So this time I'm just going to directly replace the Cartesian product with 9 queen, 9 king, and 9 2. Okay, so I got a question here. T itself is not a set of tuples, but you can look at it as a set of singleton tuples if you want to. So that's the part where I'm a little bit fuzzy on whether we should look at a singleton item as a set or as a tuple, or versus it is not a tuple. All right, so we're almost done here. Okay, so now all we have to do is to say, oh, wait, so we are just making a big, huge union of these things, right? And we know there are no overlap between the items that we are making a union out of. So now we just say, okay, so it's just now a straightforward copy and paste, okay? And here's the other one, starting with this. Copy and paste. Copy and paste. And the last one is maybe another copy and paste. There we go. All right, so are there any questions about this process? How I sort of, step by step derive omega 2 of t when t has 4 cards to begin with: queen, king, 2, and 9. I don't really care, whether it's spade or heart or whatever. I'm just using that I'm just using this as an example. Any questions? Because once we understand how omega 2 relates to omega 1, then we can, kind of jump into the recursive definition. Okay, if there are no questions, then I'm going to try to make a generalization here. So I'm going to rewrite omega 2 of t as follows. Okay, so it's a big U. Okay, so it's a big union where E is an element of T. Okay, and what we are making union out of would be described in here. It's a singleton set of E, whatever is in T, and what it is Cartesian product, what it is making a Cartesian product out of is omega 1 of t. Okay, we can see that this is really just omega 1 of t, because remember, omega 1 of t is really just t itself. But in this case, it's going to be t minus e, because e is already used here. So whatever we're making omega 1 out of, cannot have the same element. So is that okay? Does everybody see, how this is actually sort of coming out of this, which in return is coming out of this? Okay. I can sort of hear, somebody is thinking and go like, but I don't see, omega 1 of t minus, e over here. Well, that's the tail end of the recursion, because by definition, okay, we know that omega 1 of t is just t itself. So when we see t minus e, we can just say that, oh, okay, we can just look at it as omega 1 of t minus e. So now we end up with this notation, which corresponds to what I have in the text editor as the last entry here. So this is one step of generalization. I look at how omega 2 should look like, and then I recognize that as a part of how I express omega 2, there's implicitly an omega 1 in it. So from this observation, then I start to generalize. I just go like, hey, so that means it seems to make sense that if I want to figure out what is omega I of t, then all I have to do is to keep pretty much the same thing here, except instead of omega 1 of t minus e, I have omega I minus 1 of t minus e. That is, so this is a forward process of generalizing an observation into a pattern that can be applied in general, because it becomes now a recursive definition of how omega I is generated. So I'm going to let you guys think about this a little bit. I'm going to scroll back up. I don't think we're going to have time to talk about section 7, but I do want to make sure that if there are any questions right now regarding section 6, that I can answer those first before I let you guys go for the long week for the weekend. To us, it's always a long weekend because there are 5 days until we have class again on Tuesday. But I would like to answer any questions that you guys might have in the synchronous session. Okay. Yeah, so when you're studying this, it really helps to give yourself concrete examples. If you cannot understand, the concept, to the point where you can start to have concrete examples, you can go ahead and just, chat with me on Discord, and you can just go like, can you give me an example of blah, blah, blah? Because I think it's really important to tie the symbols to concepts so that you can actually, associate, okay, what is omega, representing? Oh, okay, omega is representing a set of outcomes. So, so that would be helpful. The other thing you can also do, okay, if you do not mind, working on kind of chorish kind of thing, is to take the general equation like this, and then go ahead and try to figure out, omega 3 of something, or just omega 2 of a different set. Oh, you mean the text from the editor? Yeah, I can do that. I'm gonna save it and then just post it as a file instead of copy and pasting. So let me save it to 2020 10/29. So next time I see you guys, it's gonna be November already. Man, time flies. Okay. Well, let's hope it's going to be a peaceful event. You never know exactly. I think a lot of sane people are saying that, let's hope for a landslide. Either way, it's better than not having a landslide of either direction. There we go. So we have the text from the editor, posted in Discord, and I don't see any specific questions about the topic today. So I think 5 days is great between this class and the class on Tuesday, because there's I think section 6 particularly has a lot of it's very short, okay, but at the same time, understanding what we're trying to do here can be a little bit troublesome. So I'm going to give you guys a ungraded assignment on Discord. Okay, so I'm just going to write it here in Discord. So I want you guys to help me figure out what is Q. I'm not sure whether Q2 is a good one, because Q2 is already done here. So I'll just do a Q3, but that's going to take a little bit more time. So I have to make T, only up to 4 items. Let's use the same 4 items here. So we're going to have Queen, King, 2, and 9. Okay, you cannot see it yet, because I'm working on it. So just matching parentheses right now. There we go. Oh, okay. I mistyped. I meant omega 3, not Q3. So let me fix that. All right. There we go. So you can look at this as an ungraded assignment over the weekend. At some point you're gonna go like, oh, this is a lot of typing. I get the concept already. I don't need to finish the entire thing. That's perfectly okay. Okay. But I do want you to at least work out, how Q3 relates to Q2. What does it look like, okay, before you expand Q2? Okay, that's kind of the important part. But once you get to Q2, you can expand it one more time, just a few times, because otherwise, this is going to take a little bit of. It's going to be a chore if you do the entire thing, because 4 choose 3 has. Let's see, it's 4 factorial divided by 1 factorial, so it has 24 items in it. So eventually it gets a little bit tedious. But before we get to the tedious part, okay, you kind of have to at least understand how to apply the concept. So I want you guys to at least give it a try, okay, to see if you can apply what we have learned today, and just by basically using the definition already in the notes. Okay, so I think that will help. If you have questions over the weekend, just text me. I'll get back to you as soon as I can. And then on next Tuesday, we're going to continue with section 7, and also probably move on to additional modules. So if I just take a look at the modules here, so the next module is going to be discrete probability. Which is kind of interesting, because then we are actually getting into what are the chances of something. So right now we are just generating the outcome set. Then we can talk about, okay, of the entire outcome set, only some are of interest to me. So if I want to land on the outcomes that are of interest to me, what are the chances of that happening? Then we get into interesting problems like the birthday problem. Okay, given a class of, I think this class still has 24 people officially on roster, what are the chances that at least 2 people share the same birthday? Okay, so those are the kind of questions that we'll start to examine on next Tuesday. All right, so you guys have a good weekend. Just kind of spend some time to work on the ungraded assignment posted on Discord, and I'll see you guys on next Tuesday. And right now I'm going to go back and work on my script so you can actually get to see your score for exam 1. No road today. Yep. All right. Yep. See you all next month. That's right. That is absolutely right. It's November already, man. Okay. Have a nice weekend. Mhm.